This video is part of an online course on algebra and will be about the integers. After 3 long weeks of fighting with set theoretic notation, we have finally reached a point where we can come and study the interesting bits of algebra. We are going to begin with the integers, and before we even begin, you might wonder why we need to restudy something that we learnt as little toddlers. All of us know what the integers and the simpler set, the natural numbers are. They're nothing but the set 1, 2, 3, dot, dot, dot. The set consisting of the elements 1, 2, 3 and so on and so forth is the natural numbers. Well, this definition is completely meaningless. First of all, I haven't really told you what 1, 2, 3 really are, but an even bigger issue arises. What exactly is the meaning of dot dot dot? That is a tricky thing to unravel. Because of this vagueness and essential meaningless of the definition of the natural numbers as the set 1, 2, 3 dot dot dot, we need some other way of specifying what the integers are. There are two common methods to do this. The first one is the more robust and powerful way of doing it, but it's tedious and long. What we do is we define the natural numbers in terms of set theory. So I actually tell you what 1, 2, 3, so on and so forth as sets are. One popular way to do this is to define 1 as the empty set, 2 as the set containing the empty set, and so on and so forth. Now, there is still one potential issue. This tells you what 1, 2, 3 are, but it still doesn't tell you what dot dots are. I have just shadily called dot dots as so on and gotten away with it. Well, remember in a brief video, we discussed the Zermelo-Fraenkel system of axioms for set theory. Well, one of the axioms is called the axiom of infinity. Essentially, what that axiom of infinity would say is that there is a set that consists of 1, 2, 3, dot, dot, dot. So you can sort of see that this method will require you to grapple with the axiomatics of set theory quite a bit. This is a construction that has been done in many textbooks. I had already recommended the textbook by Enderton. You can check that. There is also a 2-volume textbook by the Fields medalist Terence Tao on analysis. In the first volume, he does sit down and sort of construct the natural numbers from set theory briefly. You can have a look. Okay. Now, this is not the approach we are going to take. We are going to be somewhat less pedantic about the natural numbers. What we are going to do is, instead of starting from the axioms of set theory and constructing the natural numbers 1, 2, 3 rigorously, what we are going to do is, we are going to define the natural numbers themselves in terms of axioms. So what we will do is, rather than telling you precisely what 1, 2, 3 are, I am going to say that there is a set which satisfies some axioms, and the elements of those sets are precisely the integers. This is what I am going to do. So these axioms will encode the various properties of natural numbers and integers that you either picked up on your own while counting stones or looking at birds in a tree, or it was force-fed to you in a classroom. All the rules will be encoded in terms of simple axioms. It looks somewhat unfamiliar to you. I'm going to state the axioms in the next slide if you haven't gathered what I'm about to do. It looks somewhat unfamiliar to you because I will be using the full range of vocabulary that we have built in the past 3 weeks. There's a reason why we introduce groups, rings, integral domains and all that. Okay. Here are the axioms. It's just a short paragraph because everything has been stated before. The integers can be uniquely characterized as an integral domain Z in which 1 is not 0 and satisfying one additional property. Let n denote the subset of those elements that are positive. So just 1 second, I should add one word, I missed one word, as an ordered. The integers can be uniquely characterized as an ordered integral domain Z in which 1 is not 0 and satisfying one additional property. Let n denote the subset of those elements that are positive. Recall that positive means those elements that are greater than 0, and because we have required 1 not equal to 0, 1 must be greater than 0 from what we have proved in the previous weeks. So, how is this n characterized? If you take a non-empty subset of n such that 1 is in U and x plus 1 is in U whenever x is in U, then U equal to n. So, let's pause. What do I mean? Well, the integers are an ordered integral domain. That means there are two operations, addition and multiplication. Moreover, there is a compatible ordering, and it should not be a trivial thing. 1 should be not equal to 0 and one additional property should be satisfied. The subset of positive elements of the integers, which we call the natural numbers, must satisfy this induction principle. So what I have written here, that 1 is in U, x plus 1 is in U whenever x is in U, well, that is exactly it has the exact same form as proofs by mathematical induction, which you would have done no doubt in your school many times. Okay. So this last property is called the induction principle. It's actually a very, very powerful tool to prove statements about the natural numbers. Notice that this axiomatic definition does not tell me how to get the set Z. It merely says that Z is a set equipped with two binary operations as well as an ordering such that several things are true about that set Z. Okay. Now there is a conflict. In the very first slide, I said we can define the natural numbers as the set 1, 2, 3, dot, dot, dot. Now this is a hopelessly vague definition, but there is a great bit of merit in this definition. It's very intuitive, it's very appealing. In fact, if I had not indoctrinated you with propaganda for the first 3 weeks and directly began by saying that in this course n equal to 1, 2, 3, you would not have blinked. You would have never suspected that there is something that is going on that is not entirely correct. But because for 3 weeks we have been grappling with basic set theory and trying to do things properly and rigorously, if I now at this stage say that the natural numbers are precisely this, you will object. But without this propaganda, it's a perfectly intuitive definition. In fact, many algebra books just start by saying, in this course, n will denote 1, 2, 3, dot, dot, dot. We will assume that you are familiar with the various algebraic properties of n from school, and they will get on with the job of proving things about groups, rings, vector spaces. You can cover a lot of material. Now, we have proposed an abstract definition of the natural numbers as a subset of positive integers that satisfies one peculiar induction principle. It's a very precise definition. But where is the intuition? Why is this the set of natural numbers? What is going on? Why is that Z the integers? By making the definition abstract, we have gained precision but left intuition in the back garage. So we need to bring intuition back into play. Plus, there are two further objections. Why should there exist a set Z along with two binary operations and an ordering, which I am not writing down, that satisfies the definition? We have stated that it should be an integral domain, one should not be 0, there should be some peculiar property of the set of positive integers. Completely unclear why there is such a set Z along with such properties. And why is there only one such set? What if there are many sets of integers, all of which have equal validity as the set of integers? In short, we cannot conjure up the set of integers by fiat. We have to do some work, right? What I am going to do is I am going to be practical. Since this course is called Algebra and not about construction of integers, it will take an entire course to do it properly. So what I will do is the following. At the end of this week, I will show that essentially the set Z is unique. That is, there is one and only one set along with two operations and an ordering that satisfy all the properties that we have listed. But the construction of the integers from simpler objects, namely sets, we will ignore. I will not do that construction. That is too set theoretic and too tedious. But I will give you roughly a brief idea, maybe in 10 minutes in the last video, how to construct these integers. So, this is a pragmatic approach. I am not saying that I am being perfect, but I will say that wherever we are being imperfect, I am pointing out exactly where the lack of precision is. So, for the rest of this video and the subsequent videos, take it for granted that there is a unique set Z with two binary operations and an ordering that satisfies all those axioms that we have listed. Namely, that it's an ordered integral domain, 1 is not equal to 0, and the set of positive integers satisfy the induction principle. What we will do now is to see, or at least try to see and convince you that the set Z conforms to our intuitive idea of the integers. That is the aim of this video and the subsequent videos. Then in next week, we will see briefly basic number theory. Number theory is a vast branch of mathematics and it has tentacles in or touching almost every single subject of mathematics. You would be surprised what type of tools are used in modern number theory. So, we will have to be very, very brief in our treatment. We will study enough number theory to give context to the material that follows. Studying abstract rings and vector spaces would make more sense after seeing a bit about numbers and matrices. That's what we will do. Okay. So, this is just summarizing what I have been saying for the past 5 minutes. We will show that if there is a set of integers, then it is unique. Okay. Now, what we are going to do is we are going to show that the set Z, which now we all accept exists, satisfies several properties of the integers we studied in school. In fact, what we will do is we will show enough about the integers that you will be sort of comfortable calling it the integers. Okay. We will start with something really simple. 1 is the smallest natural number. That is, of all the natural numbers, 1 is the smallest. To phrase it precisely, if x is an n, then x must be greater than or equal to 1. Now, let's recall what is n. N is the set of positive integers. That is, that subset of Z where x is strictly greater than 1. X is strictly greater than 0. Okay. Now, so far in the first 3 weeks, we really did not see any difficult proof. Almost all the proof consisted of what I would like to say simple manipulation. You have a clear-cut goal, you have a clear-cut given data. At the max, you add and subtract 1 or something. That is the most complicated thing we have done so far in all the proofs. But from now on, we will be studying a structure that has fascinated humans for almost 3000 years. The earliest properties of natural numbers have been known even to the Greeks. So, this is a structure which have been studied for 3000 years, and yet humans cannot claim that we have a complete understanding. So there is great deal of learning to be done just studying the integers and the positive numbers. So what I'm going to do is, in between, I'm going to interject like this and ask questions about how one arrives at proofs of facts that we see in this course. So rather than just giving you the proof, I will sometimes pause and ask questions that will sort of clarify to you how somebody who came up with this proof actually came up with the proof. Okay, so let's think about this. This is a statement that is true for natural numbers and it's clearly false for integers. Right? Minus 3 is not greater than or equal to 1, and clearly this is not true in some arbitrary ordered integral domain. Right? So that immediately should focus your mind on that property that differentiates the natural numbers from the integers. So the only hope that we have of proving this is to use the induction principle. There is absolutely no way you can show that any natural number should be greater than or equal to 1 without applying the induction principle, simply because it's not true for a general ordered integral domain. It's not even true for the integers. Okay. Once we realize that we must apply the induction principle, the rest of the proof is a complete triviality. So this is the light bulb moment. Okay, we need to use induction. How does the proof go? Well, all of these proofs, as I have used the remark before, smell the same. You look at the set U, which is the set of all x in n such that x is greater than or equal to 1. So again, maybe I did not specify what this means, this symbol greater than or equal to means. Let me just recall, because I don't recall whether I introduced it last week. It says this means either x equal to 1 or x greater than 1. That's what this symbol is a shortcut for. Okay, so let's carry on with the proof. Consider the set U, which consists of those natural numbers that are greater than or equal to 1. Clearly 1 is there in U. Why? Because 1 is equal to 1, therefore 1 is greater than or equal to 1. And if x is in U, that means x is greater than or equal to 1. Then x plus 1 is also in U, as x is greater than or equal to 1 means x plus 1 is also greater than or equal to 1. This is a property that is encoded in the order axioms. When we saw what the definition of an ordered integral domain is, please recall that one of these either was part of the axioms or we have proved it. Okay. Thus, U must be the set of natural numbers by the induction principle. And we are done. We have shown that every natural number is greater than or equal to 1. So you see that this induction principle has some overlap with, or I would not say overlap, has some interplay with the algebraic and the order axioms to make something like this true. And we will see this interplay often in this video and the subsequent videos. Okay, now here's the thing. We have said it's an ordered integral domain such that 1 is not equal to 0 and a distinguished property of the natural numbers. Now, one of the characteristic features of the integers is that given an integer x, there is a next integer which is x plus 1, right? And crucially, there is nothing between x and x plus 1. So, in more fancy terminology, the integers are sort of discrete. They are not a continuous set, right? I am being intentionally vague but pictorial. Now, we want to at least show that this abstract integers that we have conjured up has this next element property. Now, how would you make such a thing precise? How to say that there is a next element? Well, we put it in a somewhat obscure way, but it will be immediately clear what we mean. given x comma y in the integers with x is less than y, then x plus 1 is less than or equal to y. Okay, why have we stated this in such a peculiar way? Well, what we are really saying is, given x and x plus 1, there is no y that is sandwiched between x and x plus 1. Okay. Now, there is a more tedious way of saying it, but that once translated will be straightforward. You can say that there does not exist any y in z such that x is less than y less than or equal, for all y in z, for all y in, for all y in z, it is false that x is less than y is less than x plus 1. Now, as you notice, by the way I tripped up, just stating this is a bit convoluted. So, even though this looks a bit obscure at first glance, it's a cleaner way of stating the same thing. If you have two numbers, integers, then if x is less than y, x plus 1 has to be less than or equal to y. It cannot be the case that y is in between x and x plus 1. Okay. Well, the proof of this is extremely simple. We just use some properties of ordering. Again, here you don't really require the induction principle, because this is sort of fact that is true even without that. Let's see how. Take two numbers x and y in z, and suppose that x is less than y. We have to show that x plus 1 is less than or equal to y. What you do is look at z, which is y minus x. From the various properties of an ordered integral domain, y minus x must be greater than 0. And thus, this z must be in the natural numbers. Okay? And from what we have shown before, hence z is greater than or equal to 1. Any natural number is greater than or equal to 1. So, I must correct myself when I said that you don't really require the induction principle. I was wrong. You do require the induction principle, because to show that z is greater than or equal to 1, we use the induction principle. So, though this does not require the induction principle directly, we are using it. For otherwise, this proof should work in any ordered integral domain, and it's not true in any ordered integral domain. For instance, Q, the set of rational numbers, is also an ordered integral domain, and it is patently false that there is nothing in between x and x plus 1. Okay. So, hence z is greater than or equal to 1, and it follows that y, which is x plus z, is greater than or equal to x plus 1. So, this is a very simple proof. We have just used the basic properties of ordered integral domains combined with one thing, the fact that z is greater than or equal to 1. That is the fact that 1 is the smallest natural number and any other natural number is greater than or equal to 1. So, this sort of suggests that z has this crucial feature that it's discrete. It's not a continuous set like q or the real numbers. Okay. Now, we come to an interesting reformulation of the induction principle. The induction principle is used to prove the principle of mathematical induction, which you have no doubt worked out in great detail in high school, but you might not have seen the induction principle in this form, which is called the well ordering principle. This is very important from a set theoretic perspective as well. Every non-empty subset of n has a smallest element. Well, 2 slides before we really showed that 1 is the smallest element of n, but this says that every non-empty subset also has a smallest element. Well, let's prove this. What do I mean by this? Let S subset of n be non-empty. what we really have to do is we have to find x naught in S such that for all x in S, x naught is less than or equal to x. This quantifies the fact that x naught is the smallest element in the set S. How do we prove something like this? Again, it must have dawned on you that we must use the induction principle, not only because that is the only characteristic feature of the natural numbers, but also because I already said that this is another reformulation of the induction principle. Okay, so how do we reformulate this induction principle so that it is useful here? Okay, what we do is the following. Let us, if 1 is in S, suppose 1 is in S, then clearly 1 is the smallest element, right? Because 1 is the smallest element in all the natural numbers, therefore it must be the smallest element in the smaller set S as well. So 1 cannot be there in this set. Okay. Now what you do is, so look at the subset of N, call it U, such that U intersection the set S is empty. Look at those elements of the set U, set N, such that U intersection S is empty. What we have really shown is, we have shown 1 is in U. Okay, we have shown that 1 is in U. Now what we are going to do is, why have we shown 1 is in U? Because if 1 happens to be in S, really nothing to prove. We have shown that the set N has the smallest element. So essentially this is a proof by contradiction. We are going to assume that there is no smallest element in S and then derive a contradiction. Okay. Now suppose 1, 2, 3, ... k are in U. Suppose we have shown that 1, 2, 3, ... k are in U by some mechanism. Then clearly k plus 1 is in U. Why? Otherwise k plus 1 is the smallest element. Of S. Since we are assuming that there is no smallest element of S, it must be the case that k plus 1 is also there in U. Hence, U equal to N and S is empty. Contradiction. Now, some of you might be eagle-eyed and you might rightfully object that I have used the induction principle in a way that is different from how we stated it in the axioms. In the axioms, we stated that if N is there in U, N plus 1 should also be there in U, then U will be N. But here, I have said, suppose 1, 2, 3, ... k is in U, and then argued that k plus 1 is also in U. So, I am strictly assuming more about the properties of the set U, right? I want you to work out as an exercise why exactly this stronger form of the induction principle is also true. It's an interesting exercise because it will reveal to you the nature of the induction principle. There must be some work you also do. I shouldn't be proving everything. So, please do that exercise. Why is it true that we can make this assumption that if 1, 2, 3 dot 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 k is in U, then k plus 1 is also in U. So that concludes the proof of well ordering principle. We have now shown that the induction principle implies the well ordering principle essentially. The converse is also true, and that is also left as an exercise. If well ordering principle is true, then automatically the induction principle is also true. Anyway, that exercise is not really an exercise because I will give away the answer in a couple of slides for free. Okay. Now coming back to our dear old 1, 2, 3 dot dot dot. What happened to them? We completely forgot about them. We are in an abstract set Z which satisfies some properties. Where have 1, 2, 3 gone? Well, we can bring them back. We can reintroduce our friends from our toddler age. 2 is by definition nothing but 1 plus 1. And 3 is by definition 2 plus 1. And 4 is by definition 3 plus 1 and so on. Okay. Now it should be clear to you that what we have called n is nothing but the set 1, 2, 3 dot dot dot. Of course, we cannot prove this because our definition uses dot dot dots. We have just made it vertical dot dot dots, but it should be clear to you. That what we are calling the set n abstractly is nothing but the set 1, 2, 3 dot dot dot. Okay. Now, some philosophy. As I have mentioned before, we will not only have small pauses where I try to explain how certain proofs were arrived at, I will also bore you occasionally with some philosophy. We started off with quite a simple problem asking what is the set of integers, right? And I said that the definition that integers or natural numbers is just a set 1, 2, 3 dot 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 is inadequate. Then we put some axioms and we showed some simple stuff about this. Question is, why can't we just ignore these axioms and just continue with our intuition about integers that all of us have? I mean, nobody really prevented us from counting apples just because we didn't know the axioms of natural numbers or integers. Society functioned quite well with just the integers for thousands of years without any precise definition or axioms. Why do we need to sit down and lay down axiomatics? Well, one reason is to be precise. Now, you might object. There is no such precision in physics, for instance. In physics, they don't really define what mass is. They don't really define what time is. They just carry on functioning because we can measure mass and time, right? I have a watch that allows me to measure time. I have weighing scales that allow me to measure mass. So what's the problem? As long as it can be measured, you can take it as well defined. Well, even there you can have objections. For instance, how do you know that if somebody comes up with a new way of measuring time, that it confirms with our existing notion of measuring time? Well, there is one advantage in physics that we do not have in mathematics. In physics, whatever we define is something that has to do with the real world. So worst case scenario, we can go ask Mother Nature, well, this new guy, fancy hot pants, wants to say that time can be measured using his fancy sand clock. Is he really correct? And Mother Nature will tell you, well, that sand clock is approximately correct, but the margin error is too much. You can perform experiments. So in the physical sciences, 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 in the physical sciences experiments or empirical evidence can settle disputes. But way back in the very first video where I talked endlessly about the nature of pure mathematics, we do not have this empirical evidence available in mathematics. For instance, if you take the number 10 power 1000, this number is so inconceivably large. There is nothing in the universe that would require a number this large to describe. It far exceeds the number of atoms that are there in the universe by an incomparable amount. The number of atoms in the universe is a minuscule number compared to 10 power 1000. So, there are numbers that are inconceivably large that exist in our mind but not physically in the universe. As I said, if you go out, you can see 2 apples, you can see 2 dogs, you can see 2 wolves. You do not see the number 2 in the natural world. The number 2 does not exist in the natural world. It exists only in the collective minds of all humans. Now, therein comes the need for axioms. If you have axioms, then the set of natural numbers that I am talking about and the set of natural numbers that you are talking about have to be the same, because there is only one and one set of natural numbers that satisfy all the properties that we have listed. So, even if you conceive of natural numbers somewhat differently from the way I conceive natural numbers, provided both of us agree that these are the axioms of the natural numbers, you have to accept whatever conclusion I come about the natural numbers, provided I did not make any mistake in my reasoning. So, the axioms allow us to settle disputes. It allows us to have multiple maybe intuitions about the same object, but nevertheless, we can always agree on what is the correct conclusion. In fact, there are situations where having a set of axioms is vital, even in physics. For instance, modern quantum mechanics, if you look at the axioms of modern quantum mechanics and look at some of the interpretations of what those axioms mean, there are many interpretations. The most famous one being the Copenhagen interpretation. The same set of axioms can be interpreted differently. But ultimately, experiment is the test. And it doesn't matter which interpretation you personally find more conceivable about the universe, provided you follow the axioms, you will always come to the same conclusion about the real world. So, I hope this slight detour into philosophy was not too boring and you have an idea as to why we needed to sit down and list some axioms for the natural numbers. Now, actually we listed axioms for the integers. Now I am coming to the famous axioms of Peano. This I am doing just for completeness. We don't really need this. Peano was the first person, at least I think that I am aware of, who listed down a precise set of axioms for the natural numbers. Peano was from the 19th century. Okay. Now, you would have noticed that we have taken one major shortcut in our development of the integers. That is, we have just given us a free gift of addition and multiplication in the axioms. We started off by saying that the integers is an integral domain. In fact, an ordered integral domain that satisfies something. Now, of course, this is not a free gift because we have to prove uniqueness, and as promised, I will prove uniqueness in the last video of this week. But there is another way which is somewhat in between the two ways that I mentioned in the first slide. One of the ways is to start from set theory, the other way is to just put everything in the axioms. This is sort of an intermediate thing, and it's maybe you can argue that it's more intuitive than what we have done, but at the same time equally rigorous. But I have chosen a shortcut in the interest of time. So what do the Peano's axioms tell you? Well, it is a set of axioms for the natural numbers, not for the integers. Well, what does it say? To each element n in n, there is a next element which we denote by S of n. S of n stands for successor of n. There is a special element 1 that is not the next element of any element. And if S of n equals S of m, then n equal to m. If the successor of n and the successor of m are the same, then n must be m. Finally, we need something like the induction principle. If A is a subset of n such that 1 is in A, n is in A implies S of n is in A, then A equal to n. Okay. So, these four axioms characterize the set n uniquely. You can show that there is only one and only one set n that satisfies all of this. Then you can actually define multiplication and addition of elements of n. For instance, this S function, if you notice, is nothing but n plus 1, right? So, as an example, if you want to define n plus m, you hold n fixed, you have already defined n plus 1, assume that n plus m minus 1 is defined, then define n plus m as n plus m minus 1 and the successor of that. You can define n plus m as a successor of n plus m minus 1 and then painstakingly prove from induction that this is defined on all of the integers, natural numbers, then show all the properties. For instance, you now have to show that addition is commutative, addition is associative, there is a element 0, you don't have to show there is an element 0 because we are just looking at natural numbers. Similarly, you can define multiplication and show the various properties. Okay. Once you have done all this, you can easily define what the integers are and actually sit down and show that the integers is an ordered integral domain with 1 is not equal to 0 and such that the subset of positive integers satisfy the induction principle. It's not very hard, but you can do it. Of course, you might wonder whether this exercise is going to be greatly informative. Well, it's not particularly enlightening because for the main reason that the type of things you do in the proofs is somewhat different from the type of things you do in the proofs of basic facts of number theory. It's somewhat different. It's all repeated induction of the same type. But it's not an entirely frivolous exercise simply because it's like opening the bonnet of a car and peeking in and seeing how exactly the engine works. There is some deal of interest in that. Even though we may never have to do that when we are driving a car, it's something like that. What we have done is learned how to drive a car which has a gear system, which is falling out of fashion. But digging up and actually constructing all of this is like really peeking inside the bonnet and seeing how things actually work. So, we are not going to engage in this. You can search Peano's axioms. Wikipedia will tell you at least 4 or 5 books where this is done in great detail. So, we are not going to do that. So, that concludes this video. Next video, we will see mathematical induction. This is a course on algebra and you have just watched the video on the integers.